Right, so who wants to go for this one? So, who wants to try this? Yeah, please write it. So we've got x prime is equal to 3x minus 2y plus 2z plus 1, y prime 2y plus z plus t, and z prime, y plus 2z plus e on the other side. Yes? Okay, great. So that's the system, and we're looking for functions of t. Okay, so maybe the first thing we need to do is to rewrite it as a matrix differential system. Yep. Okay. That's going to be our source term. So can you just explain quickly why you want to do the diagonalization?
So the goal is to find to diagonalize this matrix in order to simplify the solving process.
Yeah. So well, I don't know if I had you in tutorial online this week, but I said to the groups I don't want to see what I saw during first semester, where we had the same kind of thing without the source term, but we really had the same kind of systems to solve. What I saw for the final is people just writing diagonalization and with luck what they remembered from the formula. Okay, I don't want to see that anymore. I want to see why. Okay, why you are doing it, and the why just comes from. First, I really want to see those lines. Okay, if you're looking for that. If you write x as your unknown variable, I want to see the reasoning, or the reasoning why you do the diagonalization. Yeah?
So we need to find p, d, and so for that, we have to find the...
Okay, hold on. Why are you doing it? Again.
Well, because so you know that we know that A can be written like that. So we can solve this one, and we get
Yep.
And then we will do a substitution coming.
Okay.
Yes. And that will help us solve.
And then the system we obtain if we use that y variable is going to be y prime. Yeah, right. Okay? And what's good about that system that you obtain here? Why is that making it simpler to solve that? Because it's still the system.
Because of D,
Yeah.
it will be easier because it's the diagonal equation, so the multiplication will make it easier.
Yeah, yeah. But because we have a diagonal matrix, so that this system is actually made out of equations that are independent of each other. Okay? So you can solve independently each equation, including with the source term. Okay? So we can solve independently each equation and go back to the original. Okay? That's the fact that that's what the diagonal matrix does.
For that, you have to find so the value of the determinants for which, the values for which the determinant is equal to 0.
Yep.
So can you see?
I'm not sure, but I don't think there are many people watching anyway. So, yeah.
I was thinking.
Further. Sorry. I guess. Is that okay? Can you see on the side of the board? Yeah. Okay, so we get 1 and 3. Okay.
Can you erase?
Yeah, you can erase that. No. We have 2 times 3.
No, it's minus 2. It's lambda minus. We have to multiply this because
Well, that's one of the problems. For this system, you see it was simple to find the roots if you expand the determinant. You don't have to worry about finding obvious roots. Even if you do, there is an obvious root. But the way this matrix is, it's already factored with one of the roots, so you can directly find the other two. It happens that we have a double root. Okay, so why is that problematic?
I don't remember what we have to do when we have a double roots.
Well, we have to do the usual. That means finding eigenvectors.
Yeah.
But the problem is that when we have multiple roots, we may have not enough eigenvectors to make our P matrix, to have an invertible matrix. And we can't foresee that before we do it. Okay? But the idea is, when we have, in that case, a double root, if you factor completely the polynomial, you will have the 3 minus lambda to the square, so that means all times 1 minus lambda minus 1. Somewhere it has the same roots if I put it in one order or the other. So we've got a double root simply because it's 2 times the root of this polynomial. Okay? And so we can't foresee usually if we will have enough eigenvectors, so we should find 2 eigenvectors. Okay? In order to be able to create a matrix P that is going to be inverted. So 2 linearly independent eigenvectors. Okay, so if we plug the value 3, that's great. What's happening? The matrix we obtain has, well, actually 3 times the same line to some coefficient. Okay, we only have 1, it's a rank 1 matrix. Okay, so that means that its kernel, what we're looking for, the eigenspace is going to be half dimension 2. Okay, so yeah. Is that okay for the solving of this eigenvector? Of these eigenvectors? Can you erase the middle part? Okay. Next, when we plug the eigenvalue 1, we have a rank system, and of course, its kernel is going to be of dimension 1, which is what we expect. Okay. So anything collinear to this one is going to be an eigenvector. So up to that point, what have we found?
So we have found 2 elements for our diagonal decomposition, so D and B, and we still need to find B minus 1.
Yeah, but yes, sure. But then, what I wanted to try to ask was, actually, we have found everything to solve the homogeneous part of the system. Yeah. Okay? Quickly, what would be, so we had x prime equal to ax plus s, if we use the notations that I wrote first, okay? We have everything here to solve that part. Okay? What would be the solution here? The x0 that solves the homogeneous part, x0 of t. Let's maybe take 2 seconds to write it completely. If ever you have a homogeneous system, you don't have to go further. You can stop here. Okay, so what's the homogeneous solution?
A constant times x and 2.
Yeah. Okay, so I've got constants. So I'm going to need my three. I've got three eigenvectors, right? Two eigenvalues, but three eigenvectors. So I'm going just to sum constant exponential eigenvalue times t times the corresponding eigenvector. Okay? So constant exponential of 3t times my 1, 0, 0, plus constant 2 exponential of 3t again times 0, 1, 1, plus k3 exponential of t for the eigenvalue 1, and we had found negative 2, negative 1, negative 2, negative 1. Okay? Right? That's, you can always check. This formula is easy to remember, right? It's just constant exponential eigenvalue times t times the eigenvector. What we need to understand, however, is that that corresponds to x0 of t, y0 of t, and z0 of t. Okay, the homogeneous part of each of the unknown functions, right? And how do I get them? It's just a matter of reading that system row by row. Okay? I'm stating the obvious, but sometimes we need to do that just to remember why we're doing it. It means that the x0 is going to be that 1 plus 0 plus k3, well, minus 2k3 exponential of t. The y0 will be, well, I only have some k2 minus k3 exponential of t, and the z0 is going to be, I also have only k2. Okay, so this is it. Right, so if I'm just interested in the homogeneous part, this is my solution. And if I am given initial conditions for x at t0, for instance, y at t0 and z at t0, I can find the k1, k2, and k3. Okay? So if that's homogeneous part, that's it. But now it's a bit more complicated because we have this non-homogeneous part, so we have to deal with it, and for it, as you are ready to do it, we need to do the p minus 1. Okay? Right? Just write the why we're doing p minus 1, because our system okay, because in the diagonal matrix, in the basis that is given by the eigenvector, that's another way to see that, we have our diagonal system, okay, and so I have to see what my source term looks like in that basis of eigenvectors. Okay, that's why we have to multiply it by p minus. Okay, in the end, it's really a change of basis that goes from A to D and back. Okay, so that's really a change of basis when we go from X to Y, or from S to the source. I think there's an error. Yeah. Yeah.
I go to so from there I stay like that or I really pass in X
So why did you compute the P minus 1?
for equation.
Yes. So we need to get
S
was 1t exponential of t, I think. Exponential minus t, yeah. 1t exponential. Plus t, 1 plus t exponential minus t. Yes?
When you find the y prime is equal to dy plus this.
Well, this is the thing with this first. And you extend that. Okay? We put y prime is y is equal to p minus 1x, y prime p minus 1x prime, and p is p minus 1x. So you get the expression of y is equal to y plus 1.
Express simplified expression.
Yes? What is that?
Okay.
Yes. Yes, that's right. Okay, so what's our system in y now?
So system is
Okay, so what's good about this system? It doesn't seem much simpler as the previous one. But what's good about this system? Maybe keep. Oh, we are this. Yeah, what's good about this system is that actually, if you expand that and write it line by line, you're going to get y prime 1 is equal to 3y1 plus 1 minus t plus e of minus t. I'm writing exactly the same thing. I'm just writing each line of that matrix equation. And then you get y2 prime 3y2 plus t over 2 plus e of minus t over 2 and y3 prime is equal to y3 plus minus 2 over 2 plus e minus t over 2.
No, it's over.
Okay? What's good about this one is that now I can solve that. I couldn't solve the system in X because each they were linked. Each row was linked to any other. Okay? I had x1 prime depending on x1, x2, x3. Here I've got y1 depending on the y1 plus source term. Okay? y2 depending on the y2 plus source term, and so on. Same stuff for the third one. So I can solve each line independently. Okay? So we already know that that's all going to be the exponential 3t, exponential of t. This is what I will find again here. Okay? So actually we just need to find the corresponding particular part. Yep.
So first in the homogeneous case, then
Well, homogeneous case, we know it's going to give us the exponentials. We already know them. So we just need the particular solutions.
I don't remember after that.
Okay. All right. So we've got a typical equation, typical order 1 equation. Y prime is equal to some coefficient times y plus something. Okay? So you solve for the homogeneous part, you get y0 of t. In that case, if that's a constant, right? So we already know we have our exponentials of 3t and exponential of t. And we need to solve the particular part. Okay? How do we have two ways to solve them? Variation of parameters, which works all the time. But maybe simpler here. I don't know if that's, I think it would be simpler. When we've got specific source terms like this, polynomials, exponentials, trigonometric functions, we know that we can look for the same kind of particular solutions. When you've got a polynomial, you know you can look for a polynomial. When we've got some exponentials, as long as it's not the same exponential as the one we get in the homogeneous part, we can look for the same exponential. If it's the same exponential as the one we get in the homogeneous part, you have to multiply it by t. Okay? And if we have trigonometric functions, we know we can look for trigonometric functions. Yeah? Okay, so let's do this. We've got polynomial plus exponential, so we can look for a polynomial of degree 1. So something that would be written as at plus b, or whatever letters you want, plus a constant times the same exponential. Yeah. Yeah, and then we plug that in the equation and just identify what's happening. Plus the 1 minus t plus e of minus t.
Then I dual spots.
But you saw this method last year. Or use biological because whichever is the fastest for you.
This I just do that. I dual like that.
Yes.
So for this equal to this.
Yeah, sure.
Okay.
Yeah, and then we would just need to identify coefficients of in front of terms of the same nature. Okay? Stance, degree 1, and exponential.
Where did the minus one go in the system like y1 dash? I understand the first part, but I don't know where minus one.
P minus 1, it belongs to another ball.
Ah,
Okay.
sorry.
The Oh yes, yeah, sure. You're right. There was a 3 missing here. Yeah. We have 3y, so yes, 3 times y, so we have a 3 here. So yes. Don't hesitate to talk when you see this, right? So yeah. So it changes this one. So c 4c is equal to -1. This is what was missing. Okay, that's what was missing. Yeah.
Why did you put QC plus 1?
It's this part goes here. So we've got 3C here and 1 and negative C. Yep. Okay, that's the y prime part. That's the B part, and that's the 3y. Yes. Do we need to do the other ones? I can't give you the exact correction because I didn't make the same choice for the eigenvectors. In the end, we should find the same thing. But the intermediate part, as I don't have the same P matrix of the same, so not the same P minus 1, I don't have the same P minus 1. Seems to be very coherent and consistent with what I have. Okay? Do you need us to go through the other ones? The other ones are going to be solved exactly the same way. We have order 1 polynomial, we have exponential, order 1 polynomial exponential, we proceed exactly the same way. Okay? We know that our particular solution is going to be an order 1 polynomial plus an exponential. We can even get rid of the constant, I guess. Yeah, we don't need any constant because I would have a constant and no constant to go with it. Right? So even more than order 1 polynomial, just constant times t. Right? Plus constant times the corresponding exponential. Right? And so we identify the particular part. So that's long, okay, but it's not difficult in itself. It's a process that you can lead until the end. Yes? Okay. Right. That's why we're here. What we want. We know that our particular solution will look like this. Okay? We know that it has to satisfy the equation being that one. This is the one we are solving. Okay, so it plugs that particular solution in the equation. So here we've got the right-hand side. We've got 3y1 plus the b of t that we have, that part. Okay? And here, that's the left-hand side of the equation. It's just, if this is my particular solution, then its derivative is going to be this one. Okay? And so this has to be equal to that one. Okay? They're both equal. And this is where we're doing then the identification. Terms of the same nature, constant, something times t, and something times the exponential. They must all cancel, and they must be canceling together. Okay, the exponential won't be able to cancel with some constant or some polynomial. Right? So this is it. We do the identification. We find the y1p. We can find the y2p and the y3p exactly the same way. Okay? So we can leave that to the reader. Yeah?
I don't understand, I don't know where it comes from the particular solution for
Your lesson? That says that when you've got constant coefficients, when you have constant coefficients equation, okay, like this, first order, even second order that works too, and even higher order, as long as your coefficients are constants. Okay? If your source term has the particular form of being a polynomial or being an exponential, even multiplication of exponential times polynomial works. Trigonometric functions, if you have cosines and sines, we can prove it, it's just a matter of writing it actually, that we can find a particular solution that has the same form. Meaning here we have order 1 polynomial and some exponential. So we're looking for our particular solution as order 1 polynomial, that's this part, and exponential with the same exponential. It's just the coefficient in front that is going to be different. Okay, and you see, we solved that. We found that if we looked for this particular solution, we could find it. Okay? What you can prove is that if you have two solutions for a complete equation, the only difference between those two solutions is going to be something that solves the homogeneous part. Okay? So what's the moral of that? It's that if you find a particular solution, again with constant coefficients, if you find a particular solution, it means that that's the particular solution that you would have found using variation of parameters. Okay? You wouldn't have been able to find another one. Right? So that works all the time. So there are some restrictions, like if I had some exponential of 3t, meaning if I had the same exponential as the one that solves the homogeneous part, that would be a problem. Okay, because if I plug it then in the equation, it will just cancel because it solves the homogeneous part. So when you have this specific case, you have to multiply your exponential by t. Okay, so, but all these cases are detailed in the lecture notes, so read them again, all right? But if you're more comfortable with variation of parameters, do it. Okay, I guess it would be about the same time, right? For solving variation of parameters in that case, or in or using the particular solution. Okay? That was maybe too many details. Did I answer your question? Yeah. Right. So we find y1p, you would find y2p of t, you would find y3p of t. How do we find finally the solution in x, which is what we were looking for? That's what we wrote, and erased, and wrote again, and erased again. So this is what we find. So what we know is that the system, okay, I will find the corresponding y1, y2, y3, and the three of them have the same description, decomposition. I will find if we solve each line independently, which is why we did the diagonalization for. We will find all of them like this, okay? All the three y unknowns are going to be like this. Okay, right, I haven't written much here. Just saying that for each of these differential equations, I can find the homogeneous solution and the particular solution. Each of them, we know what it looks like. This one, k1 exponential of 3t. This one, k2 exponential of 3t. No reason that we have the same constant. And that one, k3 exponential of t. Okay, so in the end, when I just need to rebuild the solution in x, I have found completely my y unknown, I just have to go back to x. Okay, and x is, well, we have this relation between x and y. This one, okay? Y was defined as p minus 1 times x. This is what we defined earlier. So x is just p times y. So the p matrix I already have it. In my p matrix, I've got my three eigenvectors. Okay, so that's my p matrix. And I've got my y, that has those two parts. So maybe I can write those two parts separately. Y is going to be the y0. plus the yp, so the y0 part okay, plus the yp part is the one that I've erased, at least for the y. The one that contains, I don't know if somebody can tell me what we have found here?
T over 3 minus 2 over 9.
Go again, please.
T over 3 minus 2 over 9 minus 1/4 ratio minus.
Okay, so you have found this one, you will find the next two particular solutions. And this is it. We just have to write finally what are my my x of t would be. Okay, so again, I've already written earlier what the homogeneous part is. It's still the same. So I've got K1 E of 3t, and then I've got minus 2 K3 E of t, and then I've got this matrix times that vector. Okay, so which gives me, well, at least I can begin writing that. T over 3 minus 2 over 9 minus 1 over 4 E of minus, well, minus 2 times y3p, so that's actually y2p and y3p. Okay, and so on. Maybe I will write my solution here, but you see how you can reveal that. I will just write what I have found. Okay. All right. So I find minus 20 over 9 minus 5 over 3t minus exponential minus t. And then for the other one, I find so 0 times this one time. Okay, so well, that's not very interesting to rewrite this, but this is, if you want to go to till the end, which is what we would like to do at least once. Okay, that's why I didn't put more exercise like this. You just need to do it once. I hope you understand how it works, and you would be able to redo that. Okay. And there is another question in that same exercise. The initial conditions. So the three initial conditions that are given are 1, I guess, I think. Yes. Yes? Oh yeah, what did I say? Yeah, it's, so we've got K1 times this one, K2 times this one, so what we've got K2 plus K3 minus K. Okay, but it's really the same. You see, you remember how we can view matrix vector multiplication. It's going to be that first coefficient times that first column plus second coefficient times the second column. Okay? So K1 E3T times 1, 0, 0. K2 E3T times 0, 1. That's a plus 1. That should be a plus 1. And K3 E3T times minus 2. Yes, minus 1 plus 1. So that's easier to write. When you're seeing this as coefficient times the corresponding vector. Okay, and well, this is what I found. I think I checked that, so I think it's all right. Okay, so this example again is just for us to lead at least it once until the end. The end being near, because the next thing we need to do is find the corresponding initial condition. Well, we have the initial condition, so now we can find the constants, right? So my initial condition was given as value is 0. So we get x of 0 is equal to 1. That's small x. Y of 0 is equal to 1 and z of 0 is equal to 1. So it gives us a system. So K1 minus 2K2 minus 20 over 9. Then we get K2 minus K3 minus 9 over 8. And then K2 plus K3 plus 7 over 8. Yeah, and you solve K1, K2, K3. Yeah?
Yeah, I just want to understand the very last step where you solve the K1 minus K2 minus.
Oh, I just plug, if I know the value 0, so I just plug the value 0 in that.
Oh,
okay? So all the exponentials are going to give me 1. So this is it. Oh, by the way, I forgot minus 1, so that's, I forgot many things. I forgot minus 1 here, thank you, and minus 1 over 2 here. No, because when t is equal to 0, that's 0. That's just the exponential that gives me 1. Wait, so minus 1. Okay, so my advice, if you want to train on that, why would you want to train on that? Because I think these are some examples, well, some exercises that are not complicated. Each step is not complicated if you understand the whole process. So this is the kind of exercise that I could give you for the final, and that I would think should bring you back some points. Okay? All right? So my advice is, do this for ordered for system of two functions, two unknowns. All right? You will probably find some tuto matrices that we have already performed the diagonalization of. Okay? So try to solve that for some systems, x prime is equal to ax plus something here, and you can check that it's working with Wolfram alpha, for instance. Okay? You give the two equations, and I think that's just the only thing you need to write, the two equations with the source term, and it solves it for you. Okay, or maybe there is a specific syntax, but it's not too complicated to find it. if you don't ask me. Okay? So train on that. Train on simple systems where you know how to do the diagonalization of your matrix. Put a source term like this kind that is simple to solve, or not, but something that you know that you will be able to check. Okay? But what I really want you to understand is that whole process. Why are we doing each of these steps? Each step in itself is not complicated, but it's the whole reasoning. Try to hold the whole reasoning until the end. Okay? Right? So that's it for that exercise. Let's also quickly do the one with the complex eigenvalues. So this one, we won't have any source term, so that's simpler, but we will have some complex eigenvalues. Okay, like the thing we did in during the CM Wednesday. Oh, I haven't written the solution, define the solution. Oh yeah, but as I didn't use the same stuff. Well, you need to, I can't give you exactly the solution. You just have to solve. This is a simple solution. Right. Okay. Someone wants to come for the complex one? Yeah, sure. Pleasure. Erase that last line. It's false. Okay. Think about what you want to do. So you had some p minus 1. I agree. Why would you like to do something with the p minus 1? Yeah. But what's the first thing that's going to simplify? Yeah. So where do you want to put the p minus 1? Yeah, you're multiplying. Yes, and so on the other side. Yes, that's it. Okay. Yes. You're nearly there. No, the white prime was correct. Yes. Okay. So when you do it, see the reasoning. Don't try to remember. Just do it. Okay. So we want to diagonalize this matrix. That always begins this way. which one are you using to expand? Yes, but which are you expanding? Usually, by default, I do it with respect to the first column, but obviously you did it with respect to... When you expand that, expanded it using, sorry, the first row. Yeah, okay. Just state it, right? So you know how to calculate the 3 determinants. We choose the row or the column that has the most zeros. So for instance, the first row. So you get plus lambda 1 minus lambda minus 1 times the other determinant. Okay, if you know how to proceed with cells, go with cells, you do it very well. It's fine.
Should I justify all the calculations or?
I don't know. If you're sure about what eigenvalues you find.
I have 2, 1 plus I, and 1 minus I.
So that looks good. Yeah, about that. If that's your, that's not going to give you the right ones. If you have this.
I have the polynomial of degree 3.
Yeah, sure. That's what we have to get. But I'm pretty sure this is not an intermediate step. Okay. Why? Because this would be something that you could diagonalize on. Anyway, just go on. Oh no, maybe I'm wrong. Maybe I'm wrong. Just go. No. Oh yeah, sure. Okay. So yeah, let's do 2 minus lambda times. We've got 1 minus lambda squared. And here we've got lambda minus 1. Okay? Right? Okay? We can factor this with 1 minus lambda. Yes, because this is plus 1 minus lambda. So we can factor. If you're expanding that and you find common factors, just keep them as is. That will give you the factorization. So we've got 1 minus lambda. We still have 1 minus lambda times 2 minus lambda. That's fine. No, don't go there. Stop. Okay, that's what I wanted to show you. This is factor. We're looking for the roots. We already know that 1 is one of the roots. And you have to find the roots of this. Just don't expand. If you have something that is factored, it's very good.
Because I didn't do the same as this.
Yeah. But this is what. If ever it comes factored like this, that's really great. That's easier. So this is not the. No, I don't have the same. So there must be an error somewhere. So what did we find? Oh, it's here. It's not lambda minus 1.
Lambda minus 2.
It's the other one. Yes, it's you. Correct that one. So that's the one that was wrong. So we've got minus 1 plus lambda minus 1. So lambda minus 2. So this is the one we will factor with. Or 2 minus lambda. You can see the factor with 2 minus lambda. So we've got the 2 as the, yeah. Yeah, that's 2. So if I factor with 2 minus lambda, here I'm going to have minus 1.
This one?
No. Minus 2 lambda. What's wrong? It's a plus 1 here.
Because you need 2 minus lambda and this is equals to minus 1.
Oh yeah, it's a plus 1. So you were right. So this is it. Woo. Okay, so we find as expected that the complex roots are conjugate. Okay, if you say minus b plus or minus I square root of 4, you get 1 plus or minus I. Okay, so as expected, the roots are conjugate, and this is exactly the thing. When you've got a polynomial of order 2 with negative delta, the complex roots are always conjugate. Okay, so it's not. Okay, so we've got eigenvalues, 3 of them. Let's find the corresponding eigenvectors. For the real eigenvalue, it's just as ever. I think you're making it much more complicated than it is. It's working, it's correct, it's the method. Yeah, but as we expect with eigenvectors, when we're looking for eigenvectors, we expect one of the lines to be redundant. Sometimes it's not very obvious because it's really a linear combination of the other two, but here it's just the opposite of the previous one. Okay, so we know that this line is not going to be useful. Okay. In any case, when you've got one simple eigenvalue, you can erase one of the lines. Okay, the other two will be used. Okay, and here what do I get? X is equal to y, and x is equal to z. Okay, so we directly find the eigenvector. Okay, but if you don't see that, don't worry. If you do the Gaussian elimination, you will find it. Okay, so what's our eigenvector that we can choose? 1, 1, 1. Then we need to find one eigenvector for one of the two complex roots. We just need one because we know that the second eigenvector for the second complex root is just going to be its conjugate. Okay, so in a way it's simpler when you have complex roots because you only have one to find. Okay, one of the eigenvectors, not the two of them.
I think I made it more complicated than. Yeah.
Let's try anyway. Okay, so again, if you want, you can do the Gaussian elimination. You can do the Gaussian elimination, but we expect it to be a rank 2 system, not a rank 3 system. So we expect one of the rules to be not useful, right? So let's assume that the second one is not useful. You can always check in the end, so that if everything fits, it means your calculations were correct. Okay, so from the first row, I can do the same thing as before. We get y is equal to I times x. From the last row, well, it works especially well when I've got some zeros on my rows, because then I've got very directly some corresponding solutions. So the first row, we say ix is equal to y. From the last row, we get x is equal to minus I times z. Plus, yes, thank you, and yeah, all right. And so let's make a choice, whichever you like. Let's put x is equal to 1. You get, what do you get? Y is equal to I, and then z is equal to 1 over I, which is simplified as minus I. Okay, right? So I get 1 I minus I. You can check that it's working, okay? If you're not sure about that, negative 1 plus 1 minus I times I. Minus I. So, yes. So that's negative 1 plus I minus I times I. That's going to be minus 1, so plus 1 minus I. So that's indeed equal to 0. That's satisfying my second row. Okay? But in general, when you're looking for eigenvectors, as you know, one of the rows is going to be redundant. Take the two most easy ones, solve that, and you can check in the end that it fits the third row. Okay? If that's too many simplifications, go with the Gaussian elimination. It will work. Okay? Just that when you get used to it, always the same tricks are working. And that's math, that's logic. That has a reason why it's working. Okay? So this is the eigenvector that we find for 1 plus I, we said? Yeah? What would be the eigenvector for 1 minus I?
1 minus I. No.
I can find it directly.
This is the same, but this is the conjugate of
It's going to be the conjugate of this one. As easy as that, that's it. When you've got complex eigenvalues, so minus I and I. So it's not the same. Yeah, of course. All right? What can we do next? first, I think we should write, if we are okay with complex solutions, we have everything we need to write the complex solution. Okay, so let me just sum up. And for 2, for eigenvalue 2, we have found 1, 1, 1. So if we are okay with keeping complex solutions, we can write the solution we obtain, right? And then we will write what we keep if we want only real solutions. Yes? Okay. So that would be, so what is that? That's our x. Okay, so the,
Is there an X or
yeah, what?
I was just wondering if
Yeah, usually I write the exponential first. But it's, yeah, it's really, it's just that usually we write because that's one real value times a vector. So usually we write real value times vector. Okay, so that's what we have. If we're okay with complex solutions, meaning we can take any complex values. Okay? But if we want to keep only the real solutions, well, we saw that in class on Wednesday. You've got the whole, we also did the proof of that in, when I went online for that. So we know we can simplify this. Okay, so what can we do? If we want real solutions.
Probably use the silence.
Yes? Okay, so the idea is that, well, if you want real solutions, you just take C1 exponential of 2t times that part is going to be real. But then we have to select only the real parts, the real solutions here. That means not selecting only the real part, but making the right choices for C2 and C3. Okay? The whole reasoning, the proof we did was actually if we take C3 to be the conjugate of C2, it will all rearrange into something that is real. Okay? And that's something that is real. Actually, we can, we have a solution for that. So we have to compute actually the real parts. Yeah, we will do it. We will do it. Okay. In the end, you have a whole proof of that again during the class last time. Or in the lecture notes, you can find it or ask me if you really need it. Okay? But in the end, when you've got these things, we will rewrite it as some arbitrary real constant times the real part of that stuff. EI 1 plus I C times my vector plus another arbitrary constant times the imaginary part. So the imaginary part is not including the I. The coefficient in front of the I of my imaginary number, of my complex number. So so the same thing. Okay, we need only one of them because they are conjugates, so it will rearrange well into that expression. The imaginary part of, so we keep again the same stuff. Okay, we just need to keep one of these combinations. Why? Because that's anyway that's the conjugate of this one, right? So it does simplify in the end like this, right? So if you need the details, we did that, right? It's a record. Okay? So we need to compute the real part and the imaginary part of that thing. Okay? Yes? So, what does it look like? First, what does it look like? My exponential of 1 plus it. This, it's easy. Well, it's easy. It's not too complicated. It's just exponential of t, 1 times t, times exponential it. So the exponential it is cosine t plus I sinus of t. Okay, so we have to find the real part and imaginary part of this times the vector 1I negative I. Yep. So to find that, we just need to extend it. So the exponential of t is going to be a big factor anyway. Yeah, we just write what we have for each row. Okay, plus row, same row. I plus t. Row. Okay, so now it's very clear what is my real part. My real part is going to be, so I've got exponential of t as a factor everywhere. Real part cos t for the first row minus sine t and plus sine t. Imaginary part, exponential of t, sine t plus t minus sine minus cos t. Okay, so we can write finally the answer using that formula. So I guess we can erase that. Yes, to check only the real solutions, the real functions that are going to look like this. Okay. Yes?
Where did the 1 plus I go?
The 1 plus I here, it was, well, it was 1 plus I times t. So it was et. It's the product of e power t to times eit, and the eit is expanding into cosine t. So well.
This is a real part.
Yeah, let's not forget that we already also had, that thing. Why do you write s? It's, yeah, I want to see it as a function of t, correct? So we have x of t, y of t, z of t, I think that were our unknowns. Yep. Yes,
The imaginary part is the still need to compute
yeah. K3 times the imaginary part of this. We can factor with exponential of t. It's going to be slightly less. And so we have sinus t, cos t, and minus cos t. Okay, so that's right. So if we're looking for x of t, it's just going to be the first row of that, y of t, second row, and z of t, this is the third row of this. Do you have any questions? So the example that I did during the class on Wednesday was a mix of these techniques and what we can do when we have higher order equations with constant coefficients, okay, that you can rewrite as a system, okay? But if you think that, where have you already seen that kind of stuff? When you were solving order 2 equations, okay, and you found that the characteristic polynomial had complex roots. Okay, you knew that you could write distributions as combinations of cosines and sines. Exponential of the real part times linear combination of cosines and sines, which is exactly what we're doing. Okay, when we only have one row, when we only have one equation, and so we don't have vectors, we're just going to have linear combination of cosines and sines. It's the same formula, actually. This is just a generalization of what you saw for order 2 equations. Okay? So we still have 15 minutes. What do you want to do? We can do some of the substitutions that we haven't done yet, or go for the second exercise, maybe another time. Okay. What? So, I propose some of the substitutions. Just ask for the ones you would like to do. What? In the 6th, substitution by the variable? I don't know where to put my page. I've done a mix. So, exercise 6, substitution of the variables. Yes, I think that would be interesting. Okay, during one of the tutorials that I did on that, I corrected quickly the first one of the 6, so we should go for the second or third one. Okay? So number 6, exercise 6, which one do you want to do? So not the first one, because I've already done that in the tutorial, so I put the video online and linked it in the Moodle class, so you can look at the last minutes of that. So second or third one? Second one. Okay? So what do we have here? Y second plus y tangent of x. Y prime times tangent. And the idea is to put t is equal to sinus of x. Okay, so somebody wants to try this one? Yes?
Minus cosine squared.
Minus cosine square. Okay. So, do you know how to start this? First thing you have to do when you write a substitution, when you're given a substitution, is to write what it means. Okay? So our unknown function, so I think my function was, the equation was not very nicely written because, yeah, I don't think I will try to write it better if I give that to you in a minute. So my unknown function is y of x. So it's a function of x. And we say, let's use substitution t, where t is equal to the sinus of x. It means that I will want to make it equal to some function, let's call this z of t. What's the relation between the two? T is equal to the sinus of x. So z of sinus of x should be equal to y of x. Okay? So sometimes your substitution will be given in another way by saying x is equal to something of t. Okay, but in the end, it's that you've got a function of x, a function of t, and you have to write in the middle what it means. Everything starts from here, because this is what we're going to expand to find the derivative, to understand what it means to have the function. Okay? In the first one, I'm sorry, I can't find the text, but, well, let me just... In the first one, we had something similar, okay? In the first one of that exercise, let me just write this as a side note. In the first one of that exercise, we had a function where y was the unknown, okay? And we said we want to use the hint is use substitution. T is equal to ln of x. Yeah, that's what we had to do. Okay, T, you should use this substitution. Here you clearly had a choice. You could use, so the idea is same stuff. You have a y of x, and you want to express what it means for z of t. Okay? So, you could go directly the same way as here, by saying if it's expressed this way, it means that t is ln of x, so that's z of ln of t. Of ln of x. Zt is actually z of ln of x, and that's my function y of x. So that when I want to plug the y prime and the y second, I just have to do d over dx and d2 over d2 dx2 of this expression. So this is where we're using the channel, okay? But if you like, some people prefer it the other way around. This substitution, you could write it in the reverse way by saying that if t is ln of x, x is exponential of t. Okay? It's a well-defined substitution if I tell you, if you know that you can go back to the original variable. So you could also use that y of x is, again, it's the same thing, z of t, but how would you express the whole stuff? Y of x is y of exponential of t. Okay? And so you would need to compute the derivative with respect to t to see what it means to do the derivative with respect to x. Okay? Here, we assume that it's going to be a well-defined substitution. If nothing is given in the exercise, we should. If that's a well-defined substitution, so we should restrict that to one of the intervals. What would be my interval so that this is a well-defined substitution? What should I choose for the interval for x so that this is a well-defined substitution? So it must be bijection. Okay? So the sinus, that's the one. Okay? So as soon as I'm getting back here or here, that's not going to work. So my substitution, well, it's going to work only on one of these kind of intervals where I have a bijection. So we must say, for instance, that x is between negative pi over 2 and pi over 2. And this way I can define sine minus 1, the inverse function. Okay, and you could work the same way here with the sign minus 1. But I guess it would be more complicated. Okay? So we should have restricted, that should have been said in the text of the exercise. X is between negative pi over 2 and pi over 2. Okay. So this being said, let's work from here. Okay? So we have this definition, and we know that we want to express this using this function, so let's go, right? That means we start from here. Y of x is equal to z of sinus of x. So I need to see what it's going to give me to calculate y prime and y second. Okay, so y prime of x, what is that going to be? Yes. Right? One of it, and then y second. Differentiate that, right? So minus sine. Z prime. Plus cos square. Z second. Okay. So now that I have calculated that, I can substitute in my equation what I have found, and hopefully that's what it was done for. That's why we gave you that substitution. It should simplify. So that second, y second is going to be cos square z second of sinus x minus sinus of x z prime of sinus x, and then we've got plus tangent y prime plus tangent cosine of x z prime of x minus cosine square of y of x to z of sinus of x. And that should be equal to 0. Okay, so let's see what's simplified. Okay, so first, oh yeah, a lot of things are going to simplify. Tangent of x times cosine of x. First, maybe I should exclude these, because the tangent couldn't be well defined, so I should exclude that, right? Okay, so tangent times the cosine. How does it simplify?
Sine of x.
Yes, sine plus sine of x. That's good, because then it's going to simplify with this one. Okay, so this cancels with that one. Okay, and actually my equation becomes much simpler. We've got cosine square of x z second sinus of x minus cos square of x z sinus of x is equal to 0. As I have excluded minus pi over 2 plus pi over 2, which was legit because I already had some tangent here. But again, this should have been said in the text of the exercise. I can divide my equation by cosine square because it's never going to be equal to 0. Okay? So that my equation now becomes very simple. It's just that second, well, I can still write that sinus of x minus z is equal to 0. Okay? And as I know that sinus of x should be equal to t, I can rewrite this as the second of t minus z of t is equal to 0. Okay, so now I just have to solve this equation in z, and then we will go back to the original value. Right, so what's the, how do I solve this kind of equation? Order 2, constant coefficient, homogeneous. Yeah, characteristic equation. Or 2 minus 1. Same stuff you would obtain if you are the opposite, but same roots as the one you get when you make the determinant of the corresponding system. Okay, if you write this for the system. Right, so r squared minus 1, so r equals to plus or minus 1. So I've got those two real roots, and then I know that my solution is going to be z of t is arbitrary constant exponential of t plus arbitrary constant exponential minus t. And this is it. I just have now to go back to the original variable, which was t psi is equal to sinus of x. Z of t is equal to z of sinus of x is equal to y of x. And so I've just got y of x. I just have to substitute back t to by sinus of x. Y of x is k1 exponential sinus of x plus k2 exponential minus sinus of x. Yep. Nope. That's it. Okay, maybe very quickly, we have 2 minutes just to find what equation, what simpler equation I get when I plug the substitution in the third one. Okay? So the third one is x y second plus y is equal to 0. X squared. And we say put t is equal to ln of x. So that's function of x. Okay, so we do as before. Y of x, in the end, should be a new function that depends on t. What comes in the middle, what depends on how you define your variables. So t is equal to ln of x, so that's z of ln of x. We do our calculations y prime, y second, and see what's happening. Okay? So y prime of x. General again. So derivative of log over x. Z prime of ln of x. Second derivative, y second of x. So multiplication or even u over v. So z second ln of x times x minus z prime ln of x divided by x squared. Whichever way, you should find the same stuff. So 1 over x multiply by x, divide by x. Okay. Okay. So z second over x squared minus z prime n of x over x squared. Okay, so now if I plug that in the equation, I forgot the square here. If we plug that in the equation, we've got x squared times y second. So we get z second minus z prime plus y of x is just z. What?
The second is prime.
Thanks. Okay, so what we did was transform a second order linear but non-constant coefficients equation into a second order constant coefficient equation, which you can solve. You do the fragment equation, r2 minus r plus 1 is equal to 0, minus 3. So you get complex roots. Complex roots 1 plus or minus I square root of 3 over 2. And so you know that your solutions k1 exponential 1 over 2t, exponential 1 over 2t cosine square root of 3 over 2t k1 plus k2 sinus square root of 3 over 2t. Okay, same idea as before, same stuff. Okay, I've got complex roots for my second order equation. So this is my solution. And finally, we have to go back to the log, to the original variable, which was t is equal to ln of x. So I just have to substitute t by the log of x. Exponential 1 over 2t, t is equal to log of x, square root of x, cosine, k1 cosine square root of 3 over 2 log of x. Okay, no other way to find this kind of complicated stuff than that. Sinus square root of 3 over 2 log of x. Yep. Okay, right, that's it. So we are back with a new chapter. Yes. Yes, that's what I brought them for. Oh, it's when I keep a very little price. Wow. Very little. 1 over x times the x. That's x over x.
Le problème, c'est surtout marquer quelque chose au début.
Oh, yeah, sure.
Ça me semble que tu dois
le 375, 425, 425, and I put it yeah, that's fine.
Okay.
No? I counted 425, so 125, 175.
This one includes this.
Yeah. At the
Oh,
top,
okay,
I just
sorry.
put the. And
I was really surprised when you stick to the.
Yeah, let's sit together.
Like, I think maybe regard on when I came out of it, I didn't feel like I had paid that much, so I don't understand why.
Il y en a au moins un en retard.
I just don't know how to do that better.
This we have done that many times in class.
Yes.
So yes, we should keep that a bit. Yeah, this I agree that would be methodology because I don't say what you prove. Okay? And for me it's like you proved nothing. We want to prove that. And what you said is we have this equality and you just extended that side. But there's no proof in showing that you really have the two things that are equal to each other. You see what I mean? Okay? And here again. I don't see what you mean. Here we have you just want the identity. Why not? But then the matrix of the map is the image of the basis vector. It doesn't correspond to them. I know it's really if you want to come back later so we can see more details.
Thank you.
So stay with us, please. I think it's you have good grades, but you are much to get. It will be a bit, whatever. But that's good. So you're respected. Okay. Do you want to see your favorites, guys? Look at them. So I actually want to see your papers. No?
Yes?
Yes? Maybe? Yes?
There's not much to see.
I have to stand them back. Okay?
Je pense même que j'arrêterai à 50.
Ah.
Vendredi, à 5h, les cerveaux vont faire.
Ouais,
Merci.
This will never work. Okay. It's supposed to be a lounge chair. Made of marble. The only thing we believe is because they only gave us this big, and this will never hold.
Maxence, c'était combien mon Maxence?
Voilà. Ah non. Salut. Je sais pas, j'ai pas raconté de bêtises non plus.